So thanks for inviting me to the workshop. So I'm going to talk about offline and online remapping workflows and what we have implemented within E3SM going forward, what we want to use. Thanks. So the work is funded primarily by the E3SM project, the DOE PER climate project. So I just want to acknowledge that. So this is a brief overview of my talk. I'll just go over some of the motivations and challenges in doing remapping and how to do conservative interpolation between component grids, and what are the strategies that we are currently implementing within E3SM, and some software updates and some results to end the talk. So solution remapping on unstructured meshes is a pretty complex process. So what we want to measure when we transfer the fields from a source grid to a target grid is some of these key metrics. So one is insensitivity to the underlying grid mesh topology. Next is a conservative projection going from source to target. Is it globally conservative or locally conservative? And consistency, which shows whether the discretization order and accuracy is preserved when we do the projection between the grids. And the next is monotonicity, which is the global maxima and minima. And you can also impose that sort of in a local sense for the local maxima and minima as well after the projection. And of course, performance plays a pretty key role when doing real world production runs. And so scalability is an important factor as well. So this is pretty complex in the sense we are trying to optimize all of these objectives in transferring the solution from a source to target in a coupled run. So within E3SM, the current state of the art is to do the offline online model. there isn't a production fully online model within E3SM. This has several bottlenecks, especially when we want to play with different types of grids, when we want to change the resolution, or when we have moving grids. It requires us to go through this offline process once again. And there are several software tools available to do this currently. We, of course, constantly use the ESMF, the regrid framework, the tool. It supports all these different interpolation schemes, and also the first and second order conservative projection as well. And more so these days, we are also leaning towards using Tempest Remap, which can do higher order conservative projection and produces consistent remaps with monotonicity constraints. And it also supports a spectral element, finite element, field data description, or finite difference or finite volume discretizations as well. Optionally, we can also use the NC remap, which kind of uses both ESMF and Tempest as its dependencies. And NC remap also has its own type of parallelization with OpenMP. And I want to mention here again that ESMF supports MPI level parallelism, but Tempest Remap does not. Tempest is a purely serial tool. And so that's one of our motivations here. How do we parallelize this tool and still gain higher order conservative maps? So we introduced this new library, Moab. Well, it's been around for some time, but so Moab stands for Mesh-Oriented Database, and it's a fully unstructured mesh data structure that provides full manipulation and queries in parallel of an unstructured grid. And so we want to use Moab in combination with Tempest Remap to provide the capability, the infrastructure for computing both the offline and the online maps. So with Moab, we have the full online computation of the conservative and monotone remaps with Tempest Remap underneath. And there is no approximation to the mesh topology or the field discretization. This is especially true if you are transferring the data directly from a spectral element grid to, say, finite volumes. And also, Moab has been shown to be scalable and It can work on arbitrary PE layouts, but works pretty well with the E3SM setups that we are constantly running. So the right figure shows an example of a PE layout for a full couple model run. And if we were going to use this infrastructure with the Moab Tempest remap stack for remapping, we created this new tool called MB Tempest. So this is an offline tool that you can run in parallel. It generates conservative maps between a source and target grid, similar in vein to the ESMF regrid tool. And it generally loads the grids on collocated PEs and computes the maps and writes it out to a script file. The online version of the same tool essentially uses Fortran compatible APIs called iMoab, which expose the underlying C++ API that is callable from Fortran code. So we have this integrated within E3SM so that we can compute online maps on arbitrary component-to-component projection and PE layouts as well. Here's some results for our scalability study that we did with a spectral element to a finite volume projection. So that's the atmosphere to ocean projection using a Zoltan repartitioner. And the figure below shows 3 different runs with the component-wise breakup of the timings. We see that there is excellent scalability on 1,000 processes or more, and it's still the computation time for the coverage mesh, which is if I have a local target grid, I need to bring in the source elements that cover all those target elements locally in that particular process, so that the intersection can be computed completely local without any other communication. So that the combination of that still remains bounded even on 1,000 processes. The matrix vector application, we can still perform quite a bit of acceleration. We haven't even tried to optimize the sparse matrix vector applications yet. And the switch to fully online computation from an offline online model is actually seamless because the underlying API is exactly the same. So there is no difference whatsoever from a consumer standpoint in using this Moab Tempest remap stack. So we published some of those results in a GMD paper recently. So there's more details about the infrastructure and the results there. I would like to point you to that. So going forward with E3SM version 2, there are some key significant changes. So we are going towards this tri-grid configuration model where we are consolidating all the different grids used in components. And what is this tri-grid? This essentially is just a cube sphere grid for the atmosphere and a lat-long grid for the land and river models, and a polygonal grid for the ocean and sea ice models. So that really simplifies the number of grids available, number of combinations to compute the remaps. And this new atmosphere to land, atmosphere to river maps, they enable closer coupling between the land and river models. So that enables us to do better physics in terms of capturing the water management, the irrigation, the inundation, and other physics, key physics components in the land and river coupling. And for the atmospheric physics, we are moving towards using a finite volume type phys grid. So in the past, in V1, we were using the dual of the spectral element grid, which essentially created as many columns as the number of GLL points. But in V2, we'll be using this 2x2 subcell. So if you look at this lower right-hand side plot, this essentially shows a spectral element 4 to a PG2 grid. And the PG2 just shows that it's a 2x2 uniform refinement of the spectral element grid. And there is an accurate mass conserving algorithm to do the projection internally within the atmosphere model that also supports regionally refined grids. The advantage of using this PG2 grid is that it reduces the total number of physics columns by a factor of 4/9. So that's a speed up of about 125% without any other core changes to the actual models. And there is ongoing studies to ensure that the physics are convergent still at that resolution as well. And so the next release of E3SM, the V2, is scheduled for September 2021, and we're working towards that. And the MOAB Tempest Remap online coupler should be available as well by then. So here's an example of the MOAB Tempest Remap support for the tri-grid configuration. This is a surface temperature projected from the atmosphere to the ocean ice grid and the land river grid, half a degree land river grid here. As I mentioned before, we were originally doing the spectral element to finite volume projection for the atmosphere ocean. Now that will be replaced with a finite volume to finite volume type projection. And the land and river models actually share the same half a degree grid in this case. So it's kind of simplifies this online remap computation quite a bit significantly. So I just want to go over some recent work that we are doing in terms of optimization. So here I'm showing an MPAS and atmosphere grid. So the atmosphere to ocean coupling is significantly easier than the ocean to atmosphere coupling because of the topological holes that kind of slow down the intersection process. So we tried 3 different type of load balancing approaches, strategies here. One is the recursive coordinate bisection, which is applying RCB independently on both of these grids. Another is using the MPAS grid as the master and using the home grid as its slave and imposing its partition. And this is done in 3D. The next strategy is to actually apply a mnemonic projection on a 2D plane and then applying the partition on that plane and still doing the master slave, like the second case. And some results here in the bottom show that the independent RCB takes about 20 seconds for an NE256 PG2 case. And for the inferred partition, that's almost 100% speed up. And for the inferred partition on the mnemonic plane, that's a 400%, 500% speed up. So that's a significant improvement in the timings. So we are going to be looking more closely into how to apply this also in the online remapping case. So some software updates. So MCT version 2.1 is going to be released next month. There are quite a few bug fixes in the rearranger and for Intel compilers. And the MOAB and Tempest remap, we just recently released versions in August for MOAB and June 2020 for Tempest remap. And there's a conda package available if you want to play with the stack. So in summary, the MOAB Tempest remap, we have it integrated with E3SM, provides a way to achieve scalable performance without sacrificing the coupling accuracy. And we have this working for the tri-grid case, and both the two-way coupled simulations. And we are doing some comparison studies as well with respect to MC decoupler within E3SM. And what we really want to do going forward also from a remapping standpoint is to also apply a property preservation in the MOAB Tempest remap to get monotonicity and to use the tri-grid inferred partition. So I just showed dual grid inferred partition before, but we want to apply tri-grid, which also includes the LAN model in there to do synchronized grid and coupled data transfers. And how do you optimize that? And since the API is kind of the same for the offline online models, we want to extend that as well to to do direct component-to-component coupling without having a hub-and-spoke type coupler in between. Also, we have been looking at some meshless methods for performing higher order remapping for scalar data. And there's been some recent work on using weighted least squares ENO and generalized moving least squares methods for this type of problems. So we'll be looking into that and also integrating that with MOAB as well to expose to E3SM. That's all I have.